So this talk is about the only signature scheme based on isogenies submitted to the NIST, and it's called SQISign. So let's start with a quick overview of mathematical notions. So don't be scared. I'm not going to get too much into the details. I just want to set the stage a little bit about the objects that we are talking about. So the starting point for us are elliptic curves that are defined by equations of the types I've shown here. And isogenies are simply morphisms between them. So for elliptic curves, think about equations, and for isogenies, and simply polynomials that will preserve the equation from one curve to the other. Here I gave an example. So as you can see, in some cases it can be quite simple. In other cases it will be quite complicated. It really depends. And an important metric of an isogeny is its degree, which is essentially the degree of the polynomials defining the isogeny. So in this case here, this is an example of a degree 2 isogeny. And the problem that is at the heart of isogeny-based cryptography is what we call the isogeny problem. So given two elliptic curves, E1 and E2, I want to find an isogeny connecting these two elliptic curves. So of course, you have to assume several things to be sure that such an isogeny exists. And later on, we will see a refined version of this problem, but this is really the idea of the hard problem that we are going to use. So once we have elliptic curves and isogenies, I can kind of build a graph where the nodes are going to be my curves and the edges are going to be the isogenies. And if I restrict to a given degree L, then I can actually create a graph with very specific property. And in the case of supersingular curves, which is essentially a family of curves, it doesn't really matter. I think I'll explain a little bit later what a supersingular curve is, but it does not really matter. But we have very nice properties about this graph, which is all connected, which has exponential size, and which is Ramanujan. And this is also important because it will give a good mixing property to this graph. So with that, I can state a refined version of my isogeny problem in the setting of degree L isogenies and supersingular curves. And in that case, the best known attack we have essentially is to do some kind of random walk inside the graph. And the complexity of that random walk will be polynomial in the size of the graph, which is exponential. So this is why we have a hard problem. Then the object that we're going to need are endomorphisms. So an endomorphism is simply an isogeny from a curve to itself. So basically, this is a loop in my graph. And in fact, supersingular curves are the set of curves with an endomorphism ring, which has a special structure lying inside a quaternion algebra. And in this case, endomorphisms can be seen a little bit like coordinates, okay? This graph that I have, essentially it's huge, and I don't really know how to navigate inside of it unless I have some coordinates. So it's a little bit like I give you a map, and then I give you exactly where you are in the map using those coordinates. So this will help you basically navigate inside the graph. And so using computations over the quaternions that I'm not going to explain, we can essentially get the position in the graph and kind of play around the graph using the quaternions. And this is what we call the Deyring correspondence. And in particular, one very interesting thing is that when we know the endomorphism ring, so the position of my two curves, E1 and E2, then I will be able to solve efficiently the isogeny problem between them. So this is really to give you an idea how important those endomorphisms are. And of course, this means that this problem, the endomorphism ring problem, the one of given a curve I want to compute its endomorphism ring, then this problem must be hard. Otherwise, as I said to you, I will be able to solve the isogeny problem. And in fact, you can show that we can show that this endomorphism ring problem is equivalent to the isogeny problem. So these two are in fact really connecting to one another. Okay, so this was like the mathematical setup, and now let's talk about the protocol in itself. So this is a signature scheme that is derived from an identification protocol with the Fiat-Shamir transform. And so it's based on those algorithms of the Dewey correspondence that I mentioned earlier, and in particular, the algorithms to translate from quaternions to isogenies. So the idea of the identification scheme is that the public key is going to be some curve, and then the secret key is the position of this curve inside this graph. So this is the endomorphism ring of the curve. And the idea of the identification scheme is that we are going to build an instance of the isogeny problem that only the prover will be able to solve, because he's the only one who knows the secret key. And for that, he's going to use the Dewey correspondence, whereas anybody else will have basically to solve an instance of the isogeny problem, which is assumed to be impossible. So yeah, the idea of the SQISign identification scheme is really all about building an instance of the isogeny problem that the signer will solve. So this gives the following picture, where I can rewrite my secret key as some path from a curve E0 that everyone knows, and where everyone knows the endomorphism ring, toward the curve EA. And then I have 3 rounds to make my identification scheme. So first, I have a commitment phase done by the prover. So he computes a commitment isogeny and publish the curve E1 to the verifier. Then the verifier will generate a challenge isogeny that he will send to the prover. And here we have the setup for our instance of the isogeny problem. And so the goal of the prover is going to find a path between EA and E2. And this is the computation of the response isogeny, which is the most complicated part of the signature scheme. And this part really involves all the quaternion stuff and Dewey correspondence algorithms. Okay, so let's analyze a little bit what we have with that. So what are the advantage and cons of this scheme? So the first thing is that it's really compact. And this is due to the good mixing property of the isogeny graph, which implies that there always is a short path between 2 given elliptic curves. And even though we are not able to find the shortest path, we are able to find a path which is short enough to have very compact signature schemes. The public keys are also very compact, since it's only 1 elliptic curve. Then we have an easy and efficient verification. So of course, this is in the framework of isogeny-based cryptography. The verification will never be as fast as lattices, codes, or multivariate schemes. But in the world of isogenies, we have something which is pretty efficient, since for the verification, one only essentially needs to recompute this isogeny sigma, and verify that it goes from the curve, the public key curve EA, to the challenge curve. And we've made a parameter choice that make this computation pretty straightforward. So it ends up being by far the simplest step in the signature scheme. And we have also somewhat stable security. So once again, it's in the world of isogenies. Because you may be aware that Psych, one of the scheme that was submitted as a chem for the NIST competition, was broken. So you may wonder why I said that the security is pretty stable, but it turns out that like the core problem of isogeny-based cryptography, that are the isogeny problem and the endomorphism ring problem, are really unaffected by these attacks. And by that, I mean that we did not have to lower or no, rather increase the security parameters or anything else. It was because Psych was based on a version of the isogeny problem with additional information, and the attack really relies on this additional information. So the security of the basic isogeny problems is still as strong as ever. And the soundness of the scheme relies on this well-understood endomorphism problem. So this part is really nice. The zero knowledge part of the proof for the identification scheme is a little more exotic. So it's not something that is really classical or well studied. And in fact, the assumption is pretty much that the scheme is secure. So this is not perfect. We do not like very much this kind of assumption, But for now, there is no reason to believe that this assumption is wrong, and this assumption was not affected by the recent attacks. So in terms of security, the situation is not perfect, but I'd say it's as good as we can hope for in isogeny-based cryptography. In terms of cons, I'd say that the signature process is very complicated and also quite slow, much slower than the verification. It's because it relies on those complicated algorithms based on the Turing correspondence, and this implies a lot of different things, quaternion stuff, elliptical stuff, and putting all of this together is quite complicated and painful, and this is why the signature is so slow. And I'd also mention the fact that some parameters, to make the scheme as efficient as possible, we need to fine-tune very much the parameters, and in fact, it requires some extensive computation. So this is not something completely trivial as well. But it has to be done only once. So this is not like a huge problem. Okay, so in terms of sizes, more concretely, SQISign is the most compact post-quantum signature scheme when you look at the public key and signature size combined. So here are examples for each security level. So as you can see, public keys are very, very small, signatures a little bit bigger, but still very reasonable. Compared to the research papers that introduce SQISign, we've gained a little bit by using different tricks. And here you can see that the secret keys are quite big compared to the other things. It's due to the fact that basically we pre-compute a lot of stuff to improve the signing time. So this is why. But otherwise, like if we don't care about efficiency, we can get pretty very small secret keys as well. So we made an implementation of this scheme, and before giving you the results, I just want to explain a little bit where we come from, because it explains a little bit also the performances that we get. So the first implementation of SQISign was done for the first paper, which was published at AsiaCrypt 2020. This first implementation was only for NIST-1 level of security, and it used pretty heavily ParyGP to make all the quaternion computations. Then there was an improvement paper published at EuroCrypt 2023, which improved several aspects of the implementation. Some are theoretical improvements on the algorithms. Then we also improved the finite field arithmetic and this type of things. Still, it used ParyGP, but it was already much faster. And the thing is that for the NIST submission, we wanted to have a reference implementation with almost no dependencies. So we had to start from scratch, essentially to remove the ParyGP dependency, and obviously to have an implementation for all three levels of security. We took the opportunity also to clean the code and to simplify some of the heuristic algorithms, because there are lots of heuristic on the quaternion part in particular. So we obtained an implementation which is not completely finalized. In particular, we have only managed to, by the deadline of the NIST, to make partly optimized implementation at NIST-1 security. And the thing is that the performances are currently worse than the EuroCrypt 23 paper, but obviously we are working to improve that, and in the end, we are pretty confident that we are going to be able to beat that eventually. So here are times that we currently have with the NIST submission implementation. So as you can see, there is a big difference between keygen and signature and the verification. So this is in millions of CPU cycles. So it's a lot slower, even for the verification, than other schemes. This is the main downside of isogenies. Still, there are some improvements to be made, and there are still a lot of work to be done on the implementation of SQISign. So first, we need to obtain a fully optimized implementation for all three levels. There are a lot of open research questions that remains. So as I said, we definitely believe that we can go faster than the Eurocube 23 paper. And there is also some ongoing research on some deeper ideas to improve the algorithms in themselves. Then there is the question of constant time. Right now, the implementation is not constant time. It's particularly hard because we have a lot of these heuristic and probabilistic algorithms involved in the quaternion computation that are very hard to estimate and to make work in constant time. More generally, the side channel analysis of SQISign is basically non-existent. So this is something that we will need to work in the future. Finally, there are also some trade-offs to explore, different variants that could make the signature faster at the cost of slower verification, or maybe a little less compact signature. So these type of things that we need to explore, see if there are some real gains to have by exploring those trade-offs. And finally, obviously, to continue the cryptanalytic effort to rebuild the confidence of the community in the harness of isogeny-based cryptography. I think people inside the community are pretty confident, at least, that if these hard problems that I explained at the beginning, like the endomorphism ring problem, are hard, then probably SQISign is going to remain secure. But obviously, I don't think that those ideas are shared by everyone in the cryptographic community. So we need to make a lot of effort to gain more build more confidence in the harness of isogeny-based cryptography. Okay, so I will stop there. Here are the materials if you want to look for yourself, see what are concretely the algorithms that we use. And we have also a website, which is pretty basic, but still you can find all the information there.